everyone, today I am going to talk about one of the most important theorems in mathematical analysis, the Heine-Borel Theorem. If you've ever struggled with the definition of compactness, this theorem will make your life a lot easier. Let me show what I mean. So, compactness, why do we even care? Well, if a set is compact, really powerful things happen. Continuous functions on compact sets achieve a maximum and a minimum, and they are also automatically uniformly continuous. These are huge results, and they all rely on one thing, compactness. But here is the catch. The definition says every open cover has a finite subcover. Think about what every means. You have to check all possible ways someone could cover your set with open sets. And there are infinitely many ways to do that. So checking compactness directly from the definition is very hard. And that's exactly where Heine-Borel comes in. It says, in Rn, a set is compact if and only if it is closed and bounded. That's it. You just need to check two simple conditions in 5 seconds. So this theorem takes something abstract and turns into something concrete. That's why it's such a big deal. Alright, let me quickly go over the definitions so we are on the same page. A set S in Rn is compact if every open covering of S has a finite subcover. Concretely, if someone hands you a collection A equals U alpha in J, a bunch of open sets indexed by J that gather covering S. And the compactness means you can always pick finitely many, U alpha 1 through U alpha k, and they still cover S. And this picture shows exactly that. S is covered by open sets, and no matter how someone arranges those open sets, finitely many are always enough. And bounded means a set S fits inside a ball B 0M, and there is an M where the norm of every X is at most M. And closed means S contains all its limit points, or equivalently, the complement of Rn minus S is open. Okay, here it is. Let S be a subset of Rn. Then S is compact if and only if S is closed and bounded. And there are 2 directions to prove. Let's dive in. The proof has 3 steps. Step 1 is the easy direction, and step 2 is the hard technical lemma, and step 3 ties everything together. For step 1, instead of proving compact implies closed and bounded, we prove the contrapositive. If S is not closed and bounded, then S is not compact. And not compact just means we can exhibit one open cover of S that has no finite subcover. So that's our job. Build a cover that breaks. First, we prove the case 1. If S is not closed, then not compact. We start with the condition of closed. If S is not closed, so there is a limit point x0 that's not in S, which means there are points of S piled up near x0, but x0 itself is missing. For each positive integer k, we can define uk equals Rn minus the closed ball b bar of x0 1 over k. The uk just means everything outside the closed ball of radius 1 over k around x0. Next, by De Morgan's law, we can get the union of uk equals Rn minus the intersection of all those closed balls. And those shrinking closed balls squeeze down to just one point, x0. So the union is Rn minus x0, which covers S since x0 isn't in S. Now we want to find a finite subcollection. So we take uk1 through ukm, and km is the largest. Their union is ukm, which misses everything within 1 over km of S0. But x0 is the limit point of S. So by the definition of limit point, we can choose epsilon equals to 1 over km. So there is an x in S, with norm of x minus x0 less than 1 over km. And the dot x just falls through the gap. So there are no finite subcover, and the set is not compact. We can look at the picture. For every subcover of UK, we can always find a ball around X0 uncovered, so S is not compact. Let's do the case 2. Suppose S is now bounded. Then for each positive integer k, we let uk equal b of 0k. It is the open ball of radius k centered at the origin. And their union is of course Rn. So this covers S. Now try to cover S with finitely many of them, uk1 through ukm. And since smaller balls sit inside bigger ones, their union is just uk, where k is the maximum of k1 through km. And that's a ball of radius k. But we know S is unbounded. So there exists X in S with norm X bigger than k. And so that X isn't covered. Hence, no finite subcollection covers S. So S is not compact. And case 1 and case 2 together give the contrapositive. We prove the first direction. Okay, now move on the heart of the proof. We want to show that a closed rectangle R equals the product of intervals a1, b1 through an, bn is compact. And we will argue that by contradiction. If R is not compact, so there is an open covering A with no finite subcover. We set R1 equals R with diameter d1, and we cut R1 in half along every coordinate. That gives 2 to the n pieces. If every piece has a finite subcover, combining them gives a finite subcover of R1, which is a contradiction. So we can get at least one piece has no subcover, and we call it R2. Then we repeat the process. We bisect R2 and get R3, and so on. We build nested rectangles R1 contains R2, R2 contains R3, where every RK has no finite subcover, and the diameter dk equals to d1 over 2 to the k minus 1. For each coordinate I, the left endpoints aik are increasing and bounded, and the right endpoints bik are decreasing and bounded. By the monocone-Heine-Borel theorem, they both converge, and the gap goes to 0, so they converge to the C value ci, and the point C equals C1 through Cn belongs to every RK. And the picture shows why the intervals converge to the point C. Since A covers R and C is in R, some U beta contains C. U beta is open, so there exists R greater than 0 with the ball CR inside U beta. Since dk goes to 0, there's a k with dk less than R. Then every point x in Rk satisfies norm of x minus c is at most the diameter Rk, which is less than R. So we can get x's in U beta. One single set covers Rk, but Rk has no finite subcover, which is a contradiction. So R must be compact. Now is the last step. We assume S is closed and bounded, and let A be an open covering of S. Since S is bounded, we can let it fit inside the rectangle R equals minus n m to the n. A covers S, but not all of R. So we let V equals to Rn minus S, the complement. Since S is closed, so V is open. Now, A union V covers all of R. R is compact by step 2. We use the important lemma we proved. So A union V has a finite subcover B prime of R. And we remove V from B prime, because V contains no point of S. So removing it doesn't matter. What's left is a finite subcollection of A that still covers S. So that's a finite subcover. S is compact. And putting all together, we can get the Heine-Borel theorem. Now we look at a quick example. The set S equals to 0 and all 1 over n, and we want to show that it is compact. First, we show it is bounded, because everything is in 0 to 1, so it is bounded. And we want to show it is closed, because the only limit point is 0, and 0 is in S. So by the Heine-Borel, it is compact. So to sum up, the Heine-Borel Theorem tells us that in Rn, the compactness means the same thing as closed and bounded. And the hard directions relies on one key lemma, which is a closed rectangle is compact. We use a beautiful bisection method. We keep halving and trap a point, then shows that only one open set can swallow everything, which reads a contradiction. And this theorem underlies the extreme value theorem and much of analysis. And these are the references I use for the proof. That's it. Thank you for listening.